Good morning, class. Welcome to the online classes for physics of class 12th. Here, this is a video for the revision of the chapter that is semiconductor devices. We are going to see what these semiconductor devices are. So remember that in the electronics, various kinds of devices have been came. So depending on the motion of the flow of the electrons, that is devices which work according to the motion of the flow of the electrons or the flow how the electrons used to get be near the energy and how can they get ejected from the energy bands and how they used to get flow. So all these are the kind of the flow of the motion of the electrons, and these motion of the flow of the electrons is when considered or dealt with the electronics. And that means electronics, and the word came that electrons, that is the flow of the electrons. So the branch of the physics deals with the flow of the electron. That devices will be electronic devices, and the branch will be considered as the electronics. So first electronic devices which came in the earlier was the vacuum tubes. You may have seen the images also that they are very much huge size particles in that the gas used to be discharged in that heat. The two types of electrodes has been used, that is heated cathode and the other one will be the anode. So cathodes and both anodes were the two types of the diodes which been used. After the triode and tetrodes were also been used. Triodes means there will be three kinds of electrodes, and for tetra means number of electrodes used to be increased at that time, and they have the bulky size and used to be get lots of voltage to be operating, and not that much reliable they were, and they have the limited life period also. So they used to be in the time period with the limited. So that was not that much useful in our electronics part. So after that, some devices came into the invention that were named as the solid state semiconductors. Means semiconductors were something the devices which behave as both, that is as a metal or as an insulator, as well as the conductors and the insulators, because the flow of the charges is not as much as the conductors and not as negligible as in the insulators. So we can just have the control on it, and we can make the flow of the charges according to our control. So what we can say that by changing there some diffusion, or by changing some extra particles or adding some extra particles to it, we can just make the flow of the charges different. Means we can increase the charges also, we can decrease the charges also, it depends on us. So that was the biggest advantage of this being used in the electronics, because the flow of the electrons can be over controlled by us. Means we can control the flow of the electrons in the semiconductor. So we can say that at the room temperatures, when it is being left, it will be behaving as an insulator. But when we take it into the highest temperature, then we can say that with the temperature, with the increase in the temperature, the conductivity of that device also increases. Means conductivity will be directly proportional to the temperature. With the increase in the temperature, conductivity of the body increases, and conductivity means the body will be showing you the conduction according to the current. So number of the charges will be increasing. That's why the current will also be increased. So here we can say that the resistivity will be very less, that's why their conductivity also can increase. But if it doesn't provide any kind of potential to it or any energy to it at a room temperature, it will have the highest resistivity, and the conductivity will be also similar to that of an insulator. That's why it is considered as much as an insulator as well as a conductor also. So it behaves as both, that's why it was named as a semiconductor. Here you can see that classification of the solids, because see in the periodic table it is a group fourth element. So you can there also you can see the names different semiconductors like gallium, it may be germanium, even silicon, germanium are the most useful semiconductors. But you can say that related to that gallium, arsenic and also used to come, but they have the different valency than this, because the tetravalent elements are only the two, that is the silicon and the germanium, which are the most useful in the semiconductor devices. So metals, we know that will having the highest conductivity, because they used to conduct very freely. That's the number of the free electrons will be the highest. Here the conductivity will be in the range of the 10 to the power 2 to 10 to the power 8 times. Means you can say that if a number is having the number of the zeros increasing to the right side of it, then we can say that it's have the highest value. And if we talk about 10 to the power minus 2 to 10 to the power, means their resistivity is very low. If you talk about the resistivity on the insulators, then it will be very high as compared to that of a conductivity, because it doesn't have the large number of the free electrons to conduct. If we talk about semiconductors, then we know that they behave as both. That means their resistivity and conductivity in between the insulators and the conductors. That is, their resistivity is 10 to the power 5 to 0, means it can have a resistivity of 0 also, 10 to the power 0 also. Because of metals, it is 10 to the power minus 2. But here, somewhat more than that of the conductors. But it is okay for the resistance for making it as an electronic device. If we talk about conductivity, then it is given as 10 to the power minus 5 to 0. That is what the value of the resistance and the conductivity of the semiconductor devices. So what is the main features or the characteristics of the semiconductors were that they have a much higher resistivity than the metals. They have much higher, but this is less than the insulators also. So we can conduct the electrons in the semiconductors, and we know that the resistivity of semiconductors can decreased with the temperature, because we know that the temperature and the resistance are almost proportional, or we can say that they are related to each other, because you may have seen the heat or the Joule's law effect also, that the temperature and the resistance are totally related to each other. So we can say that the conductivity is increased along with the temperature, then the resistivity will be decreased along with the temperature. So we know the different types of elements also, like elemental semiconductors means the pure semiconductors which being used in our devices, that are silicon and germanium. The first device which are being used and the most used also, because the efficient semiconductors are the silicon and the germanium. And if you talk about the compound semiconductor, then the mixture of the 2 to 3 pure semiconductors, that is cadmium sulfide, you can see here, then it's gallium arsenide, cadmium selenium, and indium phosphides are also there. These all are the types of the inorganic but are the compound semiconductors. Then we talk about the organic, then the polypyrrole is there, polyaniline is there, but these are not being used in our electronic devices, but they are used in the format of sheets, like paper LEDs. You may have seen the organic LEDs have been coming. For that, this type of polymers are being used in the future. Now it is not in the use. Now we are talking about the energy bands. Now what these energy bands are? Remember that we have the electronic configurations for an atom, because in atom the centermost particle is your nucleus, and inside the nucleus the protons and the neutrons are being exist, and outside the nucleus there are some elliptical orbits being used in which electrons used to get revolve and rotate also. So that electronic configuration tells us that number of electrons present in that 3D orbitals, not in the orbit, so that in the orbitals. So that SPDF orbitals also may have learned that the number of the maximum electrons will be according to their shells. So we can say that the atoms valency will be equal to that of the number of the electrons present in the outermost shell, that are the valence electrons. So number of valence electrons will be equal to that of the electrons which are present in all these are considered as the valency. So whatever the electrons which are in the outermost shell, means the valence electrons, they will be present in the outermost shell. And if we talk about the energy bands, remember in the energy band, the down one, the lowest band was considered as a valence band, and the highest band, or the top one, is considered as a conduction band. So in that valence band, the valence electrons are used to be there, which are being bonded with the nucleus, because they are in the last shell but not that much bonded, but they are bonded with the nucleus itself. But as we provide the energy or the temperature, it will get excited from its valence band to the conduction band, and there will be some gap between these valence band and the conduction band according to the element. It will depend that what the difference is there in the energy bands, that is valence and the conduction band, and that gap between these two bands are considered as an energy band. And whatever the electrons which are to be ejected or emitted from this valence band to the conduction band, then we have to give some energy, then that potential which you are going to provide, so that should be less, and whatever the consumption of the voltage will be less, and it will be more useful for us. So we are using that kind of materials for electronic devices which have a very low energy band gaps. If we talk about the conductors or metals, these energy band gap is really less, means there is no energy band gap in the conductors, because this lowest valence band and the highest conduction band are totally overlapped with each other. And if we talk about the band gap in the insulators, and it is very high, that means the energy band gap is almost the maximum in the insulators. And if we talk about the semiconductors, the range of the energy band gap is in between the metals and the insulators. It will be in between the both. So the value of the energy band gaps Eg will be in between the insulators and the conductors. Okay, sorry for the disturbance of the sound. due to the surrounding one. So the gap, the energy band gaps or the reasons which in between these two energy levels is considered as energy gap, and the valence electrons are almost occupy the highest energy band in the valence band, and as you provide a energy or a potential to it, it will get excited to the next band, that is the conduction band. And here you can see this is the metal, that is the overlapping of the conduction and the valence band. But if we talk about the insulators, and there is a low, means their energy band gap is more than 3 electron volt, so you cannot even try to give that much potential so that the electrons can get ejected from the valence band and get moved to the conduction band. So that's why we used to consider as insulators, because cannot conduct the electricity. Similarly, if you talk about the insulators and the metals, semiconductors are in between this, means the energy band gap will also be in between the metals and the insulator, that is more than the metals but will be less than that of the insulators. So semiconductors are something whose energy band gap is less than 3 electron volt, but if you talk about the pure semiconductors, remember that their energy band gap is, for silicon it is 1.17 and for germanium it is 0.74. Okay, so remember that energy band gaps. Now if you talk about Fermi energy or Fermi level, the highest energy level, that is in the conduction band, because we know that the top layer of the energy band of the valence band, the free electrons, or we can say the valence electrons, are there. As you provide the energy, these electrons get free and get emitted from the top valence band and go to the lower band of the conduction band. So lower band of the conduction band means it's get free, and whatever the potential you are providing should be equal to that of the energy band gap, and that much electron volt if you provide to it, it will jump and will be conducting the conduction band, they are in the conduction band. So in the conduction band they have to move in the top layer, that means they require a potential. So that highest energy level in the conduction band will be considered as a Fermi level, and the energy corresponding to it will be considered as a Fermi level energy. Now this is for the valence bond model of the intrinsic, the extrinsic semiconductor. Remember, semiconductors mostly divided into the two part on the basis of how they conduct. The one is the intrinsic semiconductor, other one is the extrinsic. Intrinsic semiconductor means the pure semiconductors like silicon and the germanium, pure one which we used to get out through the earth. But if we add some impurities to it, so that we can increase the conductivity of the semiconductors, like pure semiconductor, it may be in between the conductors and the insulators, but as you provide some energy to it or the potential to the external source, then it will get ejected from the valence band to the conduction band, and we can make them the conducting very fast than that of an insulator. So it depends on us that how much conductivity we will be providing or how much the impurities we have to add, so that it can increase the number of the charge carriers. Okay, so first we will see the valence bond model of the intrinsic semiconductors. Germanium and silicon both you can have, but they will be looking out the same. But we know that the valency of the semiconductors are always been the 4, because they are in the 4th group elements, and they are considered as a tetravalent atoms. So we know that the 4 electrons that are present in the valence shell of a germanium or a silicon, if we get bonded along with that other pure semiconductor, they will again make a covalent bond with the other pure semiconductor. There is no free electron or a free vacancy is left in the bonds. So what we can say, they will attain a purest semiconductors. With the neighboring structure, they will be interact with the whole. But we know that as the temperature increases, because we know that at the lowest temperature they will be not having any free kind of electrons, they are having not number of the free electrons, so we can say that they will behave as an insulator, because they are already all the electrons are covalently bonded. But if we increase the temperature, raise the temperature, what will happen, that when we raise the temperature, the valence electrons increases, that means the covalent bond can be break, and some electrons used to get free. If you talk about the energy band, and this valence band electrons will move to the conduction band, and here the covalent bond will break out and a electron get free to conduct electricity. And as they move out from the place where they are being, like if you take any electron from here, that's 4 covalent bonds, the electron will get some energy and will get ejected to the next energy level, and they will leave a space over there. So that vacant space or the interstitial site which been left out by a electron, that is vacancy given out by the electron, is considered as a hole, and these holes are just due to the deficiency of the electron, that was considered as a positively charged. And if you talk about electron, we know that they are negatively charged. So remember, if we have to increase the number of electron in any structure, then we should have other element whose number of electrons should be more than that of a semiconductor. We know that they are tetravalent, so the valency or the valence electrons present in the other element should be 5. So we require some fifth group element so that it can provide an extra electrons to the structure. So their number of electrons will be free, then we have to add some pentavalent impurity. And if we talk about the hole, that means if we have to increase some holes in any structure, then we will need some trivalent impurity whose valence electron should be less than that of a semiconductors. So there are the two types of charge carriers. One is the electron, other one is the hole. Hole are nothing but they are just a vacancy or interstitial space which are given out by the electrons, and this space is almost filled out by the electrons itself. So they are positively charged. We just maintain that they are leaving, the electrons are leaving out from there, or there is deficiency of a negative charge, that's why they should be positive. We are assuming it out. So we know that the density of electrons and the holes are used to be same in a pure semiconductor because we are not adding any kind of the impurity. So on basis of that, we came to know that on increasing the temperature, the covalent bond can be break out, number of valence electron can get free and can move in the interstitial space itself, but they are leaving a space which was considered as a vacant space, and that was a hole. So these holes and electrons both are responsible for the flow of the electricity in the particular crystal. So this semiconductor, what we can say that the number of the free electrons and the holes are both are required for the flow of a electron, means the flow of the current. So you can see the energy band diagram, that is for the intrinsic semiconductor. That is when it is equal to that of the 0 Kelvin, it behaves like an insulator, but as we increase the temperature, we know that the bands used to break out and the electrons get free, that is they can jump out through the energy band gap. So on increasing the temperature, the number of the electrons in the conduction band will be equal to that of the number of the valence bands that are present in the holes, because we already gave that the energy band gap, the bottom one, that is valence band, is covered with the electrons, that is the valence electron. When they get some extra potential, that means when we are increasing the temperature, these valence electrons will get into the free condition, that means they become the free electron and can move on from a valence band to the conduction band. And as they move to the conduction band, now the conduction band is totally filled with the electrons, and the down, that is the valence band, is now filled with the holes. So if you talk about the intrinsic semiconductors, they cannot have a predominant hole, not an electron, because any one kind of charge carrier should have the dominance, but that was a limitation for the intrinsic semiconductor. They are used to be, means in intrinsic charge carriers, if we require an electron or a hole, we have to give some heat energy to it, means they are thermally generated. So they are not that much available for, they are not that much time limitation will be there, they are not that much flexible, not that much available also. So to increase it, we should almost add some impurities which should be permanent, so that the electrons cannot easily eject out from anywhere. So on adding some impurity, we require two kinds of impurities, that is one is the pentavalent, other one is the trivalent. On the basis of that, means when we add the pentavalent impurity to the pure semiconductor, it can be considered as an n-type semiconductor. N is a negative, because when we add some pentavalent impurity, we are giving an extra electron to the element. As number of the electron is increasing, the negatively charges are increasing, so it is negatively charged semiconductor, which was named as n-type semiconductor. When we add the trivalent impurity, means now the electron is deficient in that, means they are having the 3 valence electrons, and semiconductor diagram has 4 electrons, so there will be a left of space from the free electron, which was considered as a hole, that means they are positively charged, so they are named as a p-type semiconductor. So p and the n-type. Now the next two types of semiconductors which we are going to do, they are the extrinsic semiconductor. Because intrinsic for the pure, we are not adding any kind of impurity to it, but extrinsic has something, when we add some impurity, they will consider as a two types, which were the p and the n-type semiconductor. And the process of adding these impurities, it may be of a pentavalent, it may be of a trivalent. These process of adding impurity is considered as doping. So doping is a process of adding some desirable, whatever we require, that impurity to the pure semiconductor to increase its conductivity. So the method of dopings are different kind, because pure substance of the molten semiconductors have been diffused with the impurity. Sometimes we used to add some dopant atoms into the semiconductor by diffusing it or by bombarding the ions of the dopant atoms. So there are different kind of process for adding this doping or adding the impurities. So the two types of dopants are the pentavalent and the trivalent. If you talk about pentavalent, they are arsenic, antimony, or a phosphorus. So they used to donate the one electron to the interstitial space, so they are considered as a donors. And trivalent impurities, they are less electrons, they are providing a hole to the electrons, so they used to get some electrons to be filled with that space, so they are considered as acceptors. So here you can see this n-type semiconductors structure, that is valence bond model, that whenever you add some pentavalent impurity to that covalent bonds of the silicon structure, then we know that they are tetravalent, so they will have the 4 covalent bonds with the 4 electrons present in the pentavalent impurity. But the 5th valence electron, it will get free and will be moving in the interstitial space of the semiconductor. So due to this extra 1 electron in the interstitial space, it is considered as negatively charged. So the majority charge carriers in the n-type semiconductors are the electrons. So what we can say, that the density of the electron is more than that of the density of the holes. So we know that thermal process or whatever the temperature process will be there, along with this addition of the impurity, there will be some generation of holes and electrons will be continuously, but the holes are less as compared to that of the electrons, because we already added the impurity, so number of electrons are already increased, so the density of the electrons will be more than that of the density of the holes. And if we add a trivalent impurity, the 4 electrons of the silicon will make the covalent bond with the 3 electrons present in the trivalent impurity, but the 4th electron space will be left. That means there is a vacant space in the covalent bonds, which is considered as a hole, and this vacant space is positively charged since there is a deficiency of the electron, so it is considered as a hole. That is means in the p-type semiconductors, the positive charge is more, so they are named as p-type, and their majority charge carrier are holes, minority charge carriers are the electron. That means density of holes is more than that of the density of the electron. So this is what the recombination which I have told in the class also, that is the density of the electrons and the hole. When they get recombined, there will be the correct can flow. So the rate of the recombination will be given by the NENH. And if you talk about coefficient, that is recombination coefficient, is given as capital R. But this is for extrinsic semiconductor. Now for intrinsic, we know the density of the electrons and the holes is same. So both of they will be recombined with each other with the same speed. So that will be Rni square, because Ni, that is the density of electron holes, will be equal to that of the charge carriers, total charge carriers. So from there we got the formula for NENH is equals to Ni square, that is the recombinations value. Here you can see the energy band diagram of a p-type and the n-type semiconductors. For you can see this n-type in the left side, that is the energy band gap is there. If we are having the conduction band and the valence band is already filled with the valence electrons, so they will be eject out from their place and will come into the conduction band. But the electron which already get free due to that pentavalent impurity is already in the conduction band. So the number of the electrons in the conduction band will be more than that of the valence band holes. So the majority charge carriers are electrons. But here you can see the down level in the and donor level ED, it is given as the down level of the conduction band. Here the ejected electron from the space will be coming. And if you talk about the p-type semiconductor, here you can say that the holes are present, means the electrons which are ejected out from the valence band to the conduction band, they are already there in the conduction band. When they leave the space, they are getting the positive holes also in the valence band, but the extra impurity which we have added, they are also in the valence band. So the number of the holes are more there in the p-type semiconductor. So holes are nothing but the deficiency of the electrons or the interstitial space which are given out by the deficiency of an electron. Thus a vacancy which is created by the removal of an electron. We know that its charge is also same as that of an electron itself, but the positive and negativity, that means one is deficiency of a charge and one is a more of that charge. So this was a conductivity formula, because we know that there is a reciprocal to that of the resistivity, and resistivity can be given as the mobility, that is the mobilities of electrons and the holes. So Ne mu E, that is the number density of the electrons and the mobility of electrons. Similarly, density of the holes and the mobility of the holes. Now this p and the n-type semiconductors, first working mode when they are being joined. So when they get diffused with each other, remember that the electrons present in the p-type semiconductors and the n-type semiconductors are different, because the number of the electrons in the p-type are less, and the n-type semiconductors, they are the majority charge carriers. So the majority charge carriers, here you can see that they are given in the large balls, and the smaller one, they are the minority charge carriers that being generated due to the thermal generation. Means thermalization, when it is provided, the electrons get emitted. So that condition, they are given as the minority charge carriers. But when they are just diffused over each other, that means it can be diffused also, or a single silicon, if it is doped on the twice, means they are doped on the either sides, one by the p-type impurity and other one is the trivalent impurities. That time the pentavalent impurity will make it as an n-type semiconductor, and trivalent impurity will make it as a p-type semiconductors. So on both sides the edge, means the electrons and the holes will be diffused, due to which a junction is being there, which was named as a p-n junction, that is p-type semiconductor and the n-type semiconductors being joined. And that time what will happen, that when you are not providing any external potential, at that time due to the thermal generation, this electrons and the hole pairs will be generated, and they will be moving out for the, means one hole is there in the p-type and one electron is in the n-type, which is already free. In the n-type semiconductor it is free, so they will try to recombine in that holes to fill that. So at that time the hole and the electrons get recombination, and that the neutral atom will break out, due to which there are some minority charge carriers present in the near the junction, and that minority charge carriers without any kind of majority charge carriers in near the junction creates a layer which was named as a potential layer, depletion layer. And the potential, because they are having a negative and the positive, means the charge different to that of their majority charge carriers, will provide a potential which was named as a potential barrier. Means the field applied there due to the opposes the further diffusion of the electrons on the hole is considered as the barrier field. And they will be becoming a barrier now for the further recombination of the electrons in the holes. That is what they considered as a potential barrier. And this is what the symbol you can see in the down, that is a p-type semiconductor. Dark symbol shows you the p and the line shows you the n-type semiconductor. This is something which shows you about the unidirectional flow of the electrons. This is only due to the kind of one direction, not on the other side. So this main advantage for the unidirectional flow of the electron tells us that it can convert AC into DC, because AC current is almost in the form of wave, that it can change the magnitude along with the time. But DC current is something that does not change. So just to make that AC ripples to be less, we use this unidirectional flow of current, so that it will generate a DC power itself or a DC current itself. So it is very useful in converting it AC to the DC. Main use of that PN junction was given. Now here you can see the PN junctions working. So there were arrangement when we add some circuits on it, then it was two types of arrangement, that is forward bias and the reverse bias. First one is forward, second one is reverse. That is P if it is connected to positive, N if it is connected to negative, it is considered as a forward bias condition. If P is connected to negative and N is connected to the positive, it is considered as a reverse bias situation. So forward bias situation, we are adding the positive terminal to the p-type semiconductor, negative terminal to the n-type semiconductor. Now what has happened, that when we apply a potential to the circuit, so when you are applying this negative terminal to the negative side, means the n-type semiconductor is already filled with the electrons. These free electrons will get repelled out by this negative terminal and move out to the positive terminal, and the positive terminal holes will also be moved out. That means the electrons will go and shift to the hole so that it can be filled. But the electrons which are going to fill that holes, they will also make some holes in the n-type semiconductor. Means there are some electrons and holes present in the other layers, means on the either side of the layer, means either side of the PN junction, which was considered as the depletion layer. But they are in the opposite as which can feel, but they used to get less, means the width of the depletion layer is very much less, because their recombination is stopped after getting diffused. So diffusion of electrons and holes decreases, and along with the width, and resistance across the PN junction will also be decreased, because the holes from the p electrons begins to flow, and that too towards the junction. But as the velocity exceeds that potential barrier, then the current will start flowing across the junction. But here you can remember that feeble currents used to be flow, that is milliampere, not that much feeble. But in reverse bias, the feeble current will flow, that is means in the range of the microampere. So in reverse, if it is connected, then it is N to the positive and P to the negative. At that time, the electrons get repelled out by the N type in the forward bias, but here it will get attracted due to which the width of the PN junction layer, that is depletion layer, will be increased. That means the barrier potential will also be increased, due to which the current will not be flow. Means resistance will get high, due to which the current cannot flow through the junction, and due to the majority charge carrier. But due to that minority charge carriers which are being generated due to the thermal generation can give the current, and that to very feeble current, which is considered in the format of a microampere. These are the characteristic curves. Here you can see the circuit for the joining of the forward bias condition, reverse bias condition to the PN junction diode. So here milliammeter is used, here the microammeter will be used because it is due to the minority charge carrier, the current will be due to the majority charge carrier. So increasing the potential, the current will increase as normal metals we used to see like in a Ohm's law. So it will follow the Ohm's law. But here this is something where it is in the reverse condition, means it is due to the minority charge carrier, as the potential is also very less, so it will be negative sign. So in that, if we increase the potential, then also there is no change in the current because it is very feeble and due to the minority charge carriers. But there is some voltage of that potential barrier. If we increase the potential than that potential barrier's voltage, then depletion layer can be break out, and on the breaking of that depletion layer, there are number of electrons and holes will be regenerate in the depletion layer, and due to which the current can be flowing the diode in a PN junction diode. This is what the characteristic curve together. So the voltage with which the breakdown of the junction occurs due to the more potential than that of the potential barrier is considered as a breakdown voltage, and there is a diode being used for this breakdown voltage itself. It is a Zener diode. Reverse bias, your photodiode is also being used, but it is not in the breakdown voltage, should be less than that of the breakdown voltage. So PN junction diode has always been in a unidirectional flow of the current. So this has been used so that the current can only flow in the single direction, that should be required only the DC, not the AC. So it been usually in the conversion of the AC to the DC, and that process is considered, that means the conversion of the AC current to DC current was considered as a rectification. So the rectification process is being done by the PN junction diode. Diode is a two-terminal device which was being made by the diffusion of the P and the N type of semiconductor on the silicon layer by diffusing the two types of impurities on the either sides. So on doing this, we can prepare a diode which have the two terminals. So two terminal device were considered as diode. By using the PN junction diode, we can even generate different kinds of the diodes also. So the diode is a two terminal device which will be used by the PN junction diode. Okay. So that is what the P and the N type of semiconductors. In the next class, we will be seeing some other kinds of the diodes which have been used by the help of the PN junction. Okay, so I think that you may have cleared with the topic, that is P and the N type the semiconductors. So thank you class. The further topics regarding the different kinds of diodes we will be seeing in the next one.